great to be back. This is our final in-person lecture, so we made it. And I think that we should congratulate ourselves, or at least update. Yeah, maybe. It's kind of like a celebration. I think what we're really excited about is Thanksgiving next week. And so we find out great. Well deserved. I think we should update our posterior distributions on what is possible and remind people that if we play by the rules, we can still interact. So I think everybody was safe and maybe a little bit mentally so. So when we come back, I will be doing a synchronous lecture. So I'll be doing it in the conference center over in Hutch. So you'll meet with me at the same time, 12:20, Monday, Wednesday, Fridays. I think we have 5 or 6 lectures or something after this. So I will also have it static recorded on YouTube. The live session will be helpful just in case you have chat questions. We'll come back to review session as well. You can post your questions to Slack. Apologies for last night on not being able to make review session. So difficulties with one of the automobiles. So normal stuff. Just had to go run around, go get the automobile, ran over to the shop, pick it up. And it wasn't ready yet, so miscommunicated that. So just a little bit of a hassle. No big deal. Thanks for the flexibility. Sierra, I think, has answered a few of your questions. So were your question answered?
I made it.
Awesome. I love it when it's just that. You know, okay, it's a lot of times a mistake. But yeah, those posterior probabilities on the nulls are supposed to sum to 1. You can get away with not using the logarithm in the denominator. So for that posterior probability, if you have a good computer. And so it used to be that 1,000 draws was good enough to just make everybody's computer fail. So I think I'll make it 5,000 next time, make sure everybody's computer fails. But there are some functionalities out there that do things in higher precision and you don't see as much round off there. Personally, I like to control all of that myself in my code, most often. I can also usually make my code faster by writing myself. All the little double checks everything needs to do is sometimes a little bit overboard. But however you do that problem, that's fine by me. I think Han had pointed out that there was an error in Gelfand's paper where there's an inverse sign on something. Sierra assures me that Gelfand is also wrong. We've all looked at it. Minor mistake. So it's probably a notation he's used to using and then didn't realize that it didn't match in the 2 different ways that he was playing around with it. In the normal distribution and in the Wishart update. So I think there is maybe an inverse sign off. No big deal. So this stuff happens all the time. So I probably wouldn't go and email Alan about it. He probably knows. So he's moved on. This would be 1989. All the time. Very difficult to get your papers all written up and not make a mistake. So oftentimes with papers you'll see errata or you'll see an updated manuscript. And so maybe go search that. We're going to finish up the interval test today. We're just going to talk about it briefly. We saw how the Bayesian does it. Bayesian is rather elegant with this thing. So Bayesian, wrote this down last time, I think. Just write it again. The Bayesian approach is just to integrate your posterior distribution theta between your 2 bounds right there. And I like this answer. It's not very mathematically interesting, but it's kind of a way that maybe you can circumvent the point null. And hopefully you read all my arguments, or you saw them in the last video. So I think we had debunked this p-value stuff. Maybe not. There still is a controversy from last time, and I kind of like to tell people, why don't you just interval test? Then you don't have to think about calibrating your alternative and doing all this weird stuff. I just think that question is a little bit misphrased. You know, is theta equal to theta not? I kind of like this version of it. Of course, there's subjectivity. How wide would you want to be? But I think that's the right sort of subjectivity for any question. So if you can't think about that, what are you doing? So anyway, The classical approach is a little less elegant than this. And I'll show you what's up with it in a second. I did put out an extra credit homework on the Bayesian problem. We will look at that extra credit in just a second. I'm not going to give you a lecture on it, but from my Lehman Lectures page on 11/8/2019, Sierra gave a very well-crafted lecture on this. Simulated code of the Bayesian problem. So you're trying to remember, did I do that? Yeah, it's on the computer, I'm sure. So I watched it this morning. It's really good. It kind of bleeds into the next lecture, and I say a few things in the lecture after that. Plenty of extra credit on this problem. The Bayesian problem is one of the most important problems in statistics. Does anybody know what it is? It's that whole t-test thing when you have two populations with different variances. And the t approximation to it, where you end up doing like the Sauer weight correction sort of stuff, I don't like it. So I think this is one of the biggest culprits in stats. There's a Bayesian solution to this problem, but it's basically just comparing two population groups when the variances are different. And I give you a number of exercises to compare the classical thing to the Bayesian thing. And again, go back to the Lehman Lectures if you want and read through or watch those lectures. Homework. The next homework is out. Maybe an hour or two after class. It's about model selection, and I'll show you those as well before we kick it off with the intervals. So let me just show you these different assignments. And I said the homework was out. It's due at the final, and that is December 11th. So just so we're keeping track. So send it to me before December 12th, and I'll count it. I just want to point out, again, the final exam, that's set by the university. So that's December 11th. It says 7:45, 9:45. I'll send you out a final. I'll ask that you send it back to me within 24 hours and submit all your homework with that as well. So any extra credits you have, you can send them to us all at once at the end, if you'd like. Again, ask questions as you go. Don't leave it for 2 days before, because I already know what's going to happen. So it's going to be junk, or you're just mad. Now I can't do it. So if you have good intentions about this, just get started early. One of my rules of life, just start. So the sooner you start, the quicker you finish, the better you finish.
Excellent purpose. When we will have access to a question? When we will send the assigned question, I couldn't hear you.
When do I send out the questions? It'll be on December 10th.
So, yeah.
Yeah, or like December 11th at 1 o'clock in the morning or something like that. I'll give you 24 hours for it. You'll have that time slot plus a lot more.
And you have to submit it in Slack or email it to you?
Email it to us. So just send us an email. Don't take it up and waste your time doing that probably. If you want to do it for your future, that's fine. But just write down the solutions, scan them in, take a picture with your camera. Everybody's got one of those. There's got to be a zillion different ways that you could send me your work. Long time ago, that wasn't possible, but now you've got a million different ways. Probably you're watching the report, you just scan it. So, okay. Let me show you the assignments. So this is Bayesian extra credit. It states the problem right here. So I have two different groups, X's and Y's. Maybe the means are different, and a lot of times you want to test if those two means are different. Typical Stat 101 problem, they've been doing this problem forever. Lots of discussion on this setup, even in the lady tasting tea this week. So if you're joining us for the book club, all of this stuff is discussed. And my goodness, they make it sound so confusing, because it is. There's a description of the problem. Wikipedia has descriptions of the problem. It's one of the most famous problems in statistics. So lots of different attempts to play around with it. So one-sided testing. We walk you through a little bit of this. I want you to report error rates, basically. So I want you to check to see if Neyman and Pearson have the right error rates calibrated. For the one-sided test, everything works out great. So I'll just point out. So no problem with error rates, and in fact, the Bayesian solution to this is essentially the same thing. It's in the point null case that things change a little bit. Also, in cases where the variances are different, things change a little bit if the Bayesian has a different solution. What does the Bayesian do? It puts priors on all those parameters, co-estimates everything, and maybe it gives sampling. The reason that they didn't let the variances be different, or I should say the thing that kind of mucks up the Barron-Fisher problem for the classicist is when you marginalize out these two variance parameters, it's not a t-distribution anymore if they're different. If it was the same sigma, it is a t-distribution. And so I want to just point out that t-test that you guys have studied for a long time, it's invalid. So it's close, but we already know the null hypothesis testing game that if you're off, you could reject some approximation that you're making. I think it mucks up all the error rates. So lots of extra credit on this. So 10% midterm credit, simulate everything, verify these error rates, and then do like a Bayesian test for it all. In the one-sided case, it's pretty straightforward how you do all of this. Some extra midterm credit right here if you want to do the sharp test. That one does not work nearly as well as the one-sided test. And then there's some additionals as well. So I've phrased all this in terms of the normal distribution. If you change those distributions to arbitrary distributions as well, and run these tests, tell us what happens. Turns out that Barron-Fisher thing doesn't, that salary thing isn't going to correct very well in this case. And so when things aren't normal, the typical procedure is even more wild. Anyway, play around with that. Lots of instruction here, lots of things that you can think about. I just want you to write up in a reasonable way, you know, a comparison between these different methods. You guys are going to ask me, what should I write in? I'm confused on what to turn in. You guys are grad students. Somebody tells you to write up something, you want it to be short, and you want it to be concise and neat and well outlined. And so it's really going to be the introduction, problem one, say a couple sentences about that, show your results, what your error rates are, maybe make a table. So I'm going to leave it to you, pretty open-ended. If you don't want to do this, that's fine. It's all extra credit. Again, watch the lecture on the Lehman lectures, and it'll help you if you do want to endeavor down this path. Okay, homework, new homework. So the new homework is going to be basically about model selection on a typical regression model. So this is your multivariate regression model. We've been playing around with that for quite some time now. I wrote it down pretty loosely that we could have functions of the xi's and stuff like that, so I kind of wrote it down more loosely, but basically what I'm thinking about when I'm talking about functions of the variables is maybe interactions, stuff like that. Technically, it could be, there's an infinite number of things you could consider. And so the models that I'm going to consider in this homework are semi-linear stuff with interaction terms, maybe a lot of interactions, maybe no interactions. And I'm going to give you a bunch of data that's simulated out of different versions of this model. And I'm going to ask, can you identify the model I used to generate the data? And in some of the cases, the answer is going to be yes. And in some of the cases, it's going to be very difficult. You need to know a lot about what I did. And so stuff like in the real world, you can never really figure out. There's lots of different methods for answering these questions. There's stuff like the lasso. I'd like you to look it up, but really this problem reduces to a Bayesian regression, where this part is the contribution from the likelihood, and this part is the contribution from the prior. And this would correspond to a Laplace prior or a double exponential prior. I'll let you guys read about that a little bit. I'll have some lectures when we come back on this. There's other techniques, BIC, AIC. So these are the deviance functions plus a penalty. Deviance, I'll let you look it up, but it's 2 times the minus log likelihood ratio. So if I take the max likelihood ratio, I take a logarithm of it, throw a negative sign, and multiply by 2. That's the deviance function. So it's log likelihood ratio times 2. Max log likelihood ratio. And there's some penalties that people consider. So I want you to play around with this stuff as well. There is tons of built-in software for running these procedures. So R has it, MATLAB has it, there's tons of packages. You can use them. So I don't need you to do this all by hand. I'll have more discussion on these formulations a little bit later. They're kind of pretty easy to formulate. Even easier to just look up online and run the code. It's probably supplied on the webpage. So I'm going to be giving you a lot of X's and Y's, and I'm going to ask you to figure out what my model is, and I'm going to ask you to use a lot of different tools. The more tools you use, the more happy I'll be. What I definitely want you to do is the stochastic search variable selection. I'm going to be telling you about that today. So this is the Bayesian give sampler. So effectively, we use a point mass prior on everything to update everything. I'll tell you how that works. But basically, you're just sequentially drawing from these distributions. Okay. So the problems are to run all of your procedures on different data sets that I'll supply you with. So model selection at large, lots of techniques. If there's another technique that you want to compare, go ahead and include it. Point out to me that you picked out something interesting to compare, and I'll give you a little bit of extra credit for it. So lots of extra credit you can get in the next couple of weeks. Write this stuff up reasonably nicely, none of that scribbled up thing with your barbecue sauce all over it, wadded up and then thrown under my door. I don't like that very much, so. Happens. Okay, so lots of stuff online for you. Let's come back around to this interval testing problem. Okay, Bayesian approach is this is going to be the posterior probability of the null hypothesis given the data. Going to be equal to that. So Bayesian Solutions is pretty easy. Keep in mind, in the point null problem, the Bayesian and the non-Bayesian are really addressing different problems. The Bayesian is saying, I'm going to compare the null to a class of alternatives that needs to be well specified. The classical solution is to calibrate error weights. Fisher would have had a problem with this. He did not like that. That's the Neyman Pearsonian camp of doing everything. If you guys are reading The Lady Tasting Tea this week, there's a big discussion about this. Neyman and Pearson also said you have to compare the rejection probabilities under the alternative hypotheses. That's the concept of power. A lot of people don't do it. So I'd say those analyses don't mean very much without a power calculation. You'll notice that in the Bayesian paradigm, everything is being compared to the alternative space. So it forces you to do exactly that. So Bayesian and the non-Bayesian go into reading. On the one-tailed test, on the one-sided test, we have a lot of agreement. And on this test right here, we have a lot of disagreement. Let me show you the paper. So I'm just going to walk you through this real quickly. Mark Shervish wrote a paper on the interval test. He considers every type of test. We'll look through it just real quickly. Okay, so I pulled this off the web. It's on our web page. This was written in 1996, so old paper. Nothing new. You guys know JSTOR? You guys ever seen this? Do you guys use it? This was the only thing going when I was in grad school. We didn't have Google stuff. So this is a big repository for papers. Sometimes what you can't find in Google Scholar, you can find in JSTOR. If you can't download it, go to the library and they'll get it for you. So you can even, if you build up a rapport with the librarians, they'll email it to you so that you don't have to pay $45 for papers or whatnot. At universities, this stuff is supposed to be free. But here's a big repository where you can pull stuff down. On campus, most of it is free. So Mark Shervish's paper, p-values, what they are and what they are not, addresses a lot of questions, but mostly it addresses the incoherence of the interval test. So he goes into a little bit of a dialogue and says, let's consider 3 different types of tests. H1 is going to be this test, so versus something's not mu naught. Is it mu naught or is it not mu naught? So they have one-sided analogs of this, and they also have a 4th test called the interval test. Right here. So that's what we're studying. They have a very simple example that they look at. And so we alluded to this example last time. But basically you get one data point from a normal model, and you know what the variance of everything is. They tell you what the variance is. So let me just show you real quickly the model that they're playing out. This is the example. So the example in play is I have one data point that comes from a normal model. Theta is equal to mu in this case. So just to be specific about that. And we have a variance in all of this, and it's 1. And so their example is built off of seeing this just one data point, and you want to do inference on what the mean of that distribution is. Is it in some interval or is it not? Now, you might say, I wouldn't be willing to do this in practice. Somebody comes in with one data point, they ask you to guess, what do you think theta is? I think theta is that data point. That's my best guess. But what this is doing is it's just simplifying the full-blown problem. If I had a whole bunch of data out of that normal distribution, I would form X bar. And I would work with that statistic, and my variance would be 1 over n. So just decrease. This is the same example mathematically, but in practice, I just wouldn't do anything with this. But in studying the asymptotics of this procedure or what the procedure does, this is a perfectly well concocted problem because they give you the variance. So that's the problem that Mark is going to play around with. Let's just look at what his results are, and I'll let you read through it. Mark goes on to tell us things that we typically know. So if you've taken a Stat 101 class, here is what you would look at if you were testing the one-sided hypothesis. So cap phi, so I guess that's phi, is the normal CDF. That's exactly what you think. And so your p-value would be computed by looking at x minus mu naught. Keep in mind we divide by our standard error. Our standard error is 1. So you don't see it appear right here. And this is the corresponding p-value that you would get. If you're doing the point null, you'd have 2 times that. So, kind of weird, it's the two-tailed test. This right here in itself shows you that p-values are not a measure of the space that you're working in. They're not a measure of the null hypothesis. One way you can tell is because a one-sided thing that's a big interval, its measure is cap phi. But when I just take the endpoint and just the point, the measure is 2 times phi. So something that's infinitely smaller has twice the measure. Hopefully you've thought about that. So that means the p-value cannot be a measure against the null hypothesis. It's something else. It's the probability of your data and more extreme data, where more extremity has been defined to be the 2 tails right here. So there's a lot more to the statement than thinking about this as a measure. Bayesian's thing they always give you as a measure. It increases in the right way and it decreases in the right way. They go on to tell you about the p-value for the for the interval test. And they work through it. So Eric Lehman, no relationship to me, worked this out in 1986. So Eric Lehman worked this out, that the p-value for everything is just that. So there's 2 different cases. Depends on where x is in relation to mu's. So if x is less than the average of the mu's, you use cap phi x minus mu1 plus cap phi x minus mu2. And if x is greater than the mean of mu's, use this other formula. I'll let you work through why that is, if you so care to. And what this test is doing, this is the uniformly most powerful test right here. So it means that the type 2 error is minimized for a fixed type 1 number. It's the typical statistical thing that people are wielding. This is the uniformly most powerful test. If you just look at it, what it's really doing is it's telling you how close x is to each one of your endpoints. And that's all this thing is doing. It's just measuring how close you are to the endpoints. And then Mark does a couple calculations for us using this. So we'll see his numbers in just a second. He says a lot of things about this. Let's see if we can spot his calculations. Maybe on the next one. Okay, here it is. So in this paragraph, this paper is online, so you can go look at it and match it. They tell you, let's consider a case where we ended up sampling x is 2.18. So they grab that value, and then they consider two hypotheses. They consider the hypothesis that theta is in this interval versus this interval. And here's what I want you to notice about these two intervals, is that the interval minus 0.82 to 0.52 completely subsumes the interval minus 0.5 to 0.5. And he's going to make a point about this in a second. He's going to actually show us something really weird. So he computes the p-value using that formula. So he says the p-value for minus 0.5 to 0.5 and this p-value, and he works them both out. And he shows us some interesting results. So I guess his results are here. Let's look at this. So he ends up computing for this thing right here that the p-value is 0.0502. Now obviously he's engineered his example to make another point to say, what do you do in this case? Clearly failed to reject if you're rejecting at the 0.05 level. Then he goes on to compute this other p-value for a larger interval, and he shows that the p-value dips and it goes down. And that's supposed to extremely bother you. If you ended up making that interval bigger and bigger and bigger, the p-value would start going up again. And so it's not monotonic as a function of the interval. And so he says that's incoherence. You cannot use the p-value as a measure of the null hypothesis. Keep in mind the Bayesian test, when I make the interval bigger, I keep making the posterior bigger, so I'm just adding positive quantities. Read through this paper. I don't think anybody uses this test in practice because it's just so obnoxious. But for me, the interval test is an important test to consider. And I think the uniformly most powerful thing to do is a good illustration of maybe why you want to be amazing. So I'm not sure that's my strongest point about all this, but it's fun to kind of think about, stare at, entertain for a while. Okay. I think we're just going to leave it there and we're going to move on to model selection. It's been a little bit preachy about Bayesians versus non-Bayesians. So let's do the thing that actually convinces most people, work through some examples, and show you how to actually wield this stuff and use it in practice. Consider this example. This is the example from the homework, essentially. Y is equal to x beta. What I'm going to ask you is which of the betas, or which of the features are important. So which of the columns of x that correspond to a particular beta are important features for explaining y. So this is the name of the game in high-dimensional regression. Is what subset of these features right here are important in predicting these y's. And the typical test that we consider is this. Is beta j equal to 0 or is it not equal to 0? So there's going to be p betas in this model. That's the dimensionality of the problem. There's n data points. And basically I'm going to walk through and I'm going to try to test all these different hypotheses. That's Bayesian model selection. And we're going to build a Gibbs sampler for doing this. So we're going to take all of that theory that we just learned in the last 2 lectures and apply it to some MC&C code. And so, what are the important features? What that means is we're testing the beta j is equal to 0 or not. If beta j is not equal to 0, it means that that feature is important in explaining the relationship in the Y's. If beta j is equal to 0, then I'm multiplying out whatever column this is. So if this one right here was a 0, or let's say the j element, what I'd be doing is I'd be taking this element right here, j column, and basically removing the data from all of that. Instead of removing the data, I'm just going to multiply it all by 0. It's going to have the same impact. So very typical regression question. If you've ever taken a regression class, the whole class was about how do you figure out which betas are important or which features are important. And we answer that question by answering this question. Now there's a lot of interesting things right here. So this is that same obnoxious question that we've confronted before. And so I'll show you how Bayesian plays around with it, but of course it's going to be subject to your prior. So the Bayesian ends up using the point mass mixture prior. And usually comes out with an MC&C scheme for sampling from all of the resulting posterior distributions. This parameter is still as critical as it ever was. So if you ended up pushing that out to infinity, and you use the Jeffreys prior, you'd be putting infinite support on the null hypothesis for the exact same reasons that we saw in the previous lecture. Remember, this is all just normally distributed stuff. So it really is the same example that we were working with. The mathematics is the same, maybe a little bit more cumbersome just because of the dimensionality of the problem. But if you know linear algebra, no problem. So this is what the Bayesian will do. So what I want to show you is how the Bayesian works out the Bayes factor for this hypothesis. Okay. So what the Bayesian is going to do is they're going to apply this prior to their likelihood function that's induced from here, and then they're going to test this hypothesis. So did it come from this component, or did it come from this component? So we need a Bayes factor for doing this. Ultimately, what we're going to want is a posterior probability of that null hypothesis. If I can compute the Bayes factor, we've got the posterior probability. There's a one-to-one relationship. So I've already worked out what the Bayes factor is for you. So let me just give you a little bit of notation. So this is all the stuff you think it is, because I have caps on this. That's all this stuff from the original problem. So those x's, and the y is what you think it is as well. And so if I ended up defining these things, and you probably recognize these, that these are those regression forms that we've already played with. So when I marginalize out all of the betas, I'm marginalizing across a distribution with this expectation and this variance. We're going to marginalize it all out. I want to give you a little bit more notation. I want you to consider this matrix right here, x minus j. And what that is it's x where I've just removed the j column from everything. That's my notation. So it's everything but that column. I'm going to define 2 variance and expectation formulas using this matrix right here. So I'm just going to be using that matrix instead of the full matrix. Same thing over here. So same formulas, but the only thing that's different is I've removed the column of the x's. That's essentially the same as zeroing out that beta. And so if you work through those marginalizations that you see in the Bayes factor, the numerator looks like this. This is the one corresponding to the null hypothesis, H naught, beta j is equal to 0. And this is the marginalization of everything under H1. I'll let you verify those for yourself. I'm not going to work them out for you here because we've essentially done that quite a few times in this class. But just to make sure you guys have the right formulas, this is it. That is the Bayes factor for testing this. So it's just some X transpose X inverse stuff, X transpose Y. But keep in mind, we didn't use the flat prior. So we have this penalizer right here. Those of you that are familiar with high-dimensional regression and Sheepo model selection tools, this is the ridge regression estimator down here. This one is the ridge regression estimator. So this is the ridge penalty. This conforms to a normal, just like that. So lots of ways to talk about the same thing, use different languages, but I'm just penalizing with a prior. Some people call that ridge regression. So I'll let you work through these right here, but these are completion of the squared terms. So you should be really familiar with this. When I marginalize over the likelihood conforming to that model, everything is the inverse of that completion of the squared term. So it's a plus up here. And we've seen these forms over and over and over again. So this is the one conforming to the null and the alternative. And you can work out the probability that beta j is equal to 0, given everything else, is equal to 1 plus that Bayes factor inverse, 1 minus pi naught over pi naught, all inverted. So that same formula that we played around with a couple times. Same relationship, doesn't change, it's just Bayes' theorem in disguise. I want to remind you what those pi's are. Those pi's are these weights right here. So you need to, if you use this prior, you need to pick psi, and you need to pick the pi naughts. So let me just ask you guys, what would you pick the pi naught to be? 1 over p. Maybe 1 over p. So you would end up saying this right here would be 1 over p. So this right here would be 1 minus 1 over p. So I'd be putting a ton of weight on the alternative model like that. I don't like that. I wouldn't do that. So I'm not going to say that people don't do it, but you're certainly not putting very much emphasis on it. It won't make that much difference if n is big, but if n is small, then there's maybe some other choices. So maybe you do that. Maybe you want to build your penalty in with p, but just keep in mind there's an auto penalty getting built in right here. So if I put a lot of parameters into the model and I have this prior, it just keeps multiplying into the likelihood. So if there's 17, let's say there's 20 betas, and if 17 of them are found to be active, not zeros, then I would have this prior multiplying into the likelihood 17 times. It's an auto-regularizer. So I see what you're doing, but I wouldn't do it this way myself. So this wouldn't be my choice, but maybe. I'm just going to say, not for my regression, but maybe for yours. What about some other choices? Keep in mind what we're looking at here. Either this or this. One or the other. Maybe a half. So maybe a half. That's what I would pick it to be. So it would be the easiest thing to defend. If I wanted to control sparse models, I probably wouldn't be controlling it just through this parameter. I'd be thinking more about that parameter. So let me ask you, how would you pick this? That's a harder question. How far do you need to be from 0 before you're going to reject that it's something different from 0? It's a regression problem. You've got to do something. So maybe estimate from the variance of the response, something like that. I kind of like that. So you're going to make me go and do a calculation, look into my data, compute something and plug it into my prior. I'm about to freak out a lot of Bayesians. You know, you're going to be a little over certain about things if you do that. Now, of course, if somebody gave you the variance, you might use it right there, and I think that would be reasonable if they told you what that variance is. But if I went and estimated the variance from the y's or something like that, or maybe the residuals, I first have to fit the model, then I have to go back and do that, and then plug it in. So it's like maybe weighted least squares of some sort, maybe something like that. Change the model. So totally change the model. Let's forget about the model that we wrote down. We'll come up with a different model and add some covariance in here. I have another solution that I usually use. Very similar to your first solution. I pick it to be 1. But I do something with the data first. No. Not bootstrap it. I mean, for fun, yeah. All data I bootstrap before I even look at it, I bootstrap it. I wouldn't do a calculation so much with it or try to do an inference. I would standardize it. So if I worked with all the x's on their standardized scale, then I might pick 1 for that frame. I do that all the time. So I work on the standardized. Similar to your first response, right? It's kind of just a little bit like, instead of trying to estimate the variance and plug it in, I'm going to transform my data so that it matches my prior variance as 1. So I'm going to let you deal with all of these issues. So the data sets that I'm going to send to you aren't going to be normalized necessarily. And they'll have some little issues in them. And I'm going to say, or what I would normally say if we kept having class until the end of the semester, is I would ask you things like, did you standardize your data? You should try that out. I may put X in there that's perfectly correlated with another X. And you'll be like, you know, I was fitting this thing and my give sampler is just going crazy. It's because there's a big ridge that your give sampler is floating around. So it's almost certain that some of these data sets I'm going to give to you, I'm going to put real world issues into them. No surprise at this point. So I'll probably build something with some multi-collinearity. No matter what you do, it'll work really poorly. So all the stuff that you should do, you should still do it. All that exploratory stuff, all that Stat 101 stuff, it's still good stuff. If you've never had a Stat 101 class, I guess this is what I say, pick the wrong class. So anyway, the things people do. Standardize your data, subtract off X bar, divide by your standard errors for all the X's. Usually that's a reasonable solution unless you think the variance is the driver. In that case, you just made a big critical error. Okay. So what I want to show you is the punchline. And we'll be going through this a little bit more as we do everything. But all the give sampler is going to do, so I'm just going to run. I'm going to initialize everything, all my data. And then I'm going to run through a for loop, just over and over and over again. So this is my big MCMC for loop. How big is this? This is like big, really big. And I don't mean 100, I mean like 10,000. So like really big, like 1 million. Now you might say, I don't have enough RAM for that YouTube. So, but big and big. Run this thing a lot. And basically what you're going to do is you're just going to march through all of these full conditional distributions. So you're going to look at the posterior distribution for beta j. So I take my likelihood that's induced from this, and I multiply it by that prior. And I'm going to hold all the other beta j's fixed for that time, and I'm going to decide if I want to select this to be a 0 or a non-zero. So this distribution, after you work through the point mass prior, is going to be a mixture distribution. Some probability is going to be coming from the 0 component, and some probability is going to be coming from the other component. How do I compute those probabilities? With your Bayes factor, by plugging it into that formula. So what I do is I compute this. I'm going to call this pi j. Just for a second, that's up here. Let me just keep it as this. Probability of beta j is equal to 0. So what we do to sample from this is I flip a point with probability beta j given everything else that formula. This thing is just 1 plus 1 minus pi naught. Pi naught. If we use Jess's suggestion, this would be 1. Bayes factor inverse. And I'll be a little bit nice. Say this is the Bayes factor for the j component testing at 0. So I'm just going to be computing the Bayes factor corresponding to the null where beta j is equal to 0 versus it's not equal to 0. So I'm going to do that. I'll take this for the j1. It's changing all the time. I invert it. So I'm going to flip a coin with this probability. If heads, so if it's a 1, then beta j t is equal to 0. There's no choices. If tails, then I have to draw beta j from the full model. So beta j is going to come from a particular normal. Do you know which normal it is? It's the one with these parameters. The one that you would have worked out anyway. So if you're just sampling that beta j. So it's going to have those two parameters in here. Just going to plug them in. You'll sample those beta j's. So what you just did is you flipped a coin with the posterior probability of coming from the null model. If it's in the null model, I know it can be beta jp. There's only one choice. If I pick from the alternative model, then I need to sample that beta j and I need to update it with the correct parameters. Those are these, the ones that you would have worked out in the first place. So it's basically just you're just using this conjugate form and multiplying it into one. And you repeat, and you repeat, and you repeat. You just keep doing this. You'll notice that in my Bayes factor, I've integrated all the betas out of everything. There are conditional forms if you can't work through the integrals, if you weren't doing something normal, you could plug in and condition on all those betas. I've integrated them out of the whole process here. And then I'm just storing these betas. Now I will point out one more thing. I don't have to do this step right here. If I just wanted to know which variables were important, all I have to do is just continue to flip this coin. If I didn't want to know what the betas were, I just want to know which ones are active, then I'm going to be looking at how many times I ended up flipping a 0 versus a 1. I'm going to spend some time covering this when we come back, so more on this later. I think the most important thing now is go enjoy Thanksgiving. So it's fantastic, and the weather couldn't be better than this. I hope it holds. Anybody have a forecast? Yeah, I don't either. Yeah, right. So it's going to change anyway. Go enjoy yourself, and congratulations to everybody for making the class fun. And I'll see you guys when I get back virtually. I will point out, classes are canceled. Campus is not closed. So we're still a running university. We just don't want to encourage people to necessarily come back. So the spirit of it is if you leave, don't go spread everything and come back. But if you stay, no problem. I'm sticking around. So I'll be around if you guys need something. Shoot me an email. You can go sit down with you, work through problems, have a discussion, whatever it is. But thanks again.